So in this video, I'll be doing another proof regarding linear independence and dependence. So right before this, I did a proof with properties of transposes, and before that I gave you some examples of linear independence, dependence, and definition. So now I'm going to do another proof example with linear independence and dependence. This one's a bit tricky. So if you don't get it right away, it's quite normal. I didn't get it right away. So let's go over it. So we have two functions, given two functions where we have f of t is equal to e, so e to the x, the function, the exponential function. We have f of t is equal to e to the rt, and g of t is equal to e to the st, where we're given that r is not equal to s, and we are to prove that f and g are linearly independent. Okay, so this is kind of a hard proof to start with at first, so you don't really know how to go about it. A trick that I usually find helpful is when I can't do a proof directly, I like to try it by contradiction. So I'll explain what a proof by contradiction is in a couple of seconds, but let's attempt a direct proof. So attempt at a direct proof. So direct proof meaning that you start with what you're given and you try to prove in this case that f and g are linearly independent. So attempt at a direct proof. So what we know is we have f of t is equal to e to the rt, and g of t is equal to e to the st. Okay, now what we want to show, we want to show that we have c1 f of t, and we have plus c2 g of t equal 0 vector. In this case, it would just be 0, since we're dealing with functions. And we want to show, so basically what we want to do, our goal is to show that c1 equal c2 equal 0, right? So that's basically what I want to show. Now, what I can do is I guess I can replace my functions with what they really are. So I have c1 ert plus c2 est, okay? And I have 0. Okay, but now I'm kind of stuck, right? Because I want to show that these two things are 0, but I can't say, okay, so let's start by assuming that this is 0, then so you can't, what you can't do, so you can't assume that c1 or c2 are 0, because that would be assuming something that you want to prove, right? So you can't do that. You can't assume the conclusion of your proof. So I can't assume that c1 or c2 are 0. So I can't go that way. What I could say, no, I don't really see a way. Maybe if I move this one on the other side, so I get c1 e to the rt is equal to c2 minus c2 the st. Okay, but now what else can I do? I could divide this side by c2 and bring that on the other side, so I could get something like minus c1 over c2 e to the st e to the rt. But then I can't ln both sides because this side is negative, right? So I can't ln both sides since left hand side is negative. It's negative, and also I actually can't divide both sides by c2, right? Can't divide both sides by c2 because dividing both sides by a number implicitly you assume that that number isn't 0, because you can't divide both sides by C2. So I can't divide both sides by C2 because that would be assuming, can't divide both sides by C2 because that would be assuming that C2 is not equal to 0. Right, so now I'm assuming that C2 is not equal to 0, so already I'm showing that it's not linearly independent. So basically you can see that doing a direct proof doesn't work. So direct proof fails. Direct proof fails. So what I'm going to do is I'm going to attempt what is called a proof by contradiction. Proof by contradiction. So in a proof by contradiction, so this is like a proof concept. In a proof by contradiction, so a contradiction is I assume that the conclusion is false. So in other words, I assume the opposite of the conclusion. So I assume that the conclusion is false and try to derive a contradiction from that. A contradiction. So you'll see in a minute what I mean by derive a contradiction. But what's nice about a proof by contradiction is that you can actually start with your conclusion now. So in my case, what I'm going to do is I assume for contradiction that F and G are linearly dependent. Linearly dependent. So that means that I have some sort of non-zero solution where when I have C1F plus C2G, that will equal 0. Where C1 or and, so either C1 is not 0 or C2 is not 0, or we can have both. C1 or and C2 are non-zero. So if I replace f and g by my actual functions, I'll get c1 e to the rt plus c2 e to the st equals 0. So now what I want to do, so my goal here is to think of a solution. Think of a solution and non-zero solution where when I add these two things up, I get 0. Well, one thing that might come to mind is let's say I say e to the rt minus e to the st equals 0. Right, so this is not so, I mean, you could think of different solutions, but this one seems a bit more promising than the others, and you'll see why. So what I'm saying is that I have 1 times e to the rt minus 1 times e to the st is equal to 0. So that might seem confusing, like why would I choose this kind of example? Well, you'll see why in a couple of seconds. Okay, so I just choose a non-zero solution where I'm saying that C1, so I'm saying C1 is 1 and C2 is minus 1, and I'm saying that that's equal to 0. Okay, so what I do now is I move e to the st to the right hand side. So what I get is e to the rt is equal to e to the st. Okay. So now what I can do is I ln both sides. Okay, I ln both sides. So what I get is I do ln e to the rt is equal to ln e to the st. So then what I get, So these sort of, so if I take ln of e to the something, I just get that something. So I get RT is equal to ST. And now, I should have probably mentioned in the question, that was an oversight on my part. I should have mentioned in the question here that t is non-zero. Okay, so t is non-zero. Okay, so in this part here, since t is non-zero, I can divide both sides by t. So divide both sides by t, and what I get is r is equal s. Okay, so that's what I get using this assumption, using the assumption that f and g are linearly dependent. Okay, so that was my proof. So that was my assumption. But let's see, what's the contradiction that I get? Well, initially I'm given that r is not equal to s. Okay, but when I assumed this thing, I got that r is equal to s. So this, in fact, is a contradiction. It's a contradiction. So that means that my assumption. So when I get a contradiction means that my assumption was false. In other words, in this case, f and g are not dependent, or in other words, f and g are independent. They are independent. So that's the best way to prove something like that. So I assume for contradiction that f and g are linearly dependent. I go through some steps. So it's important to sort of, I know it's not obvious at first, and so you might have to go over this proof a couple of times before you see it. But this is a sort of non-zero solution, right? We can agree that 1 and minus 1 aren't zero. So I take that as a solution, and because taking 1 and minus 1, like that goes with the definition of linear independence. So that matches the fact that I'm assuming that f and g are linear independent. So they're linearly dependent. So using that, I get a contradiction where r is equal to s. And so I can then conclude that f and g must be independent.